Solving Cambridge O-Levels Chemistry Paper 4 Alternative to Practical October-November 2025 Paper 41. A student separates petroleum. So, petroleum is a mixture of crude oil and whatnot. Figure 1.1 shows the student assembles the apparatus. We have a proper fractional distillating apparatus in which we have a fractionating column, then we have a condenser, we have a round bottom flask over here, we have a thermometer, we have a conical flask over here. Let's see, state the name of the apparatus that's labeled A. So we can see A is called a condenser, because the function of the condenser is simply to condense the vapors that are going to come from here and to condense them into liquid. So simply call it a condenser. The student makes a mistake when assembling the apparatus. Describe the mistake. So over here you can see that first let's start from the bottom to analyze what kind of mistake is being made. It's going to happen simply that vapors are going to be formed here. They're going to then pass through this. Thermometer is in the correct place. Then they're going to pass from here. Water in is from below. Water out is from the top. That is also correct. And then the vapors are going to pass down here. But there's a problem over here. There is a seal on the bung. On the conical flask, there's a bung attached which seals it, and that's incorrect. Why is that incorrect? Because let me explain to you the concept behind it. Because when you're going to have liquid over here that's going to be formed, there's going to be some pressure created inside because of the vapors. Okay, there might be, the liquid might convert back into vapors or whatever, it's hot or whatever thing. So there's going to be pressure created inside. And if this pressure is created inside, what is going to happen? The conical flask is going to burst, right? It's going to shatter into pieces. So you can't have it sealed. That's the problem. The mistake is the bung that's attached to the conical flask. You gotta fix it. When it is correctly assembled, the apparatus shown in figure 1.1 is used to separate petroleum into useful substances. Name the separating process. This is called fractional distillation because you have a fractionating column. And what is the basis of fractional distillation? It is that liquids are separated on the basis of their different boiling points. So all the things that are over here have a different boiling point, and on the basis of that they're going to be separated. State the property these substances have that allows them to be separated. I told you, different boiling points. I already told you that's the basic principle because of which you use fractional distillation. If they have the same boiling points, they cannot be separated because otherwise it's all going to evaporate at the same time and then boil. State the name of the piece of the apparatus the student uses to safely heat the petroleum. Petroleum is going to be like an oil kind of thing, so it's flammable. And whenever we're dealing with flammable things like any alcohol like ethanol or propanol or petroleum, what do we use? We don't heat it directly. We use electric heater because the contents of petroleum are flammable. Piece of apparatus is going to be, we don't heat it directly. Electric heater. Whenever we use something flammable, we're going to use this. Petroleum contains flammable contents which can cause a fire in the laboratory. A student investigates the temperature changes when an acid neutralizes aqueous sodium hydroxide. The ionic equation for the reaction is shown. You have an acid, you have an alkali, you're making them react to form water. The reaction is exothermic. We know this. The temperature change is used to determine the concentration of the hydrogen ions in the acid. X is 1.6 mole per dm cube sodium hydroxide. Y is an acid of concentration 2 mole per dm cube. Step 1. So what the student's trying to do is fills the burette with Y. So over here we have a burette that we're filling with Y. What is Y? Y is the acid. Stands a plastic cup inside a beaker. What do you mean by a plastic cup inside a beaker? That means you have a beaker, something like this. And in the beaker, you have a cup, something like this. That's a thermopole cup in which you drink your tea. Use a volumetric pipette to put 25 cm cube of X into the plastic cup. So now you're going to transfer 25 cm cube of your X. And what is your X? X is your sodium hydroxide. NaOH is being transferred into the cup. So over here you have NaOH and you're adding acid from the top. Measure the initial temperature effects and record it in table 1.2.1. You have a thermometer inserted inside, and this thermometer is going to measure the temperature, and obviously when you're going to add the acid, neutralization reaction is going to take place, and when neutralization is going to take place, your temperature is going to increase. Then you're going to measure the final temperature by using the formula. You're going to calculate the heat energy released, and then I don't know what you're going to do next. Okay, stirs the mixture for 30 seconds, records the temperature, repeat step 5, 6 until a total of 40 cm cube of Y is added. So Y is being added from here until he adds 40. He just continues doing this work. Complete table 2.1. You should record the student's results for 5 cm cube and 30 cm cube using figure 2.1. Subtract the initial temperature of X from each temperature recorded and determine the temperature change. All temperatures and changes should be recorded to plus minus 0.5 degrees Celsius. That's very important. 30 seconds after adding 5, 30 seconds after adding 30 cm cube of Y. Okay, 5 I need to record for 5. That is 20, 21, 22, 23, 23.5. You have to record it to a precision of 0.5. So that's 23.5. And over here, that's 25, 26, 27, 28, 29.0. Don't forget the 0 because we have to write it in plus minus 0.5. 29.0. Now we find out the change in temperature. How do you find the change in temperature? You just subtract the initial temperature, that was when 0 cm cube of Y was added, initial temperature from all your temperatures. So first, 20.5 minus 23.5. That's how you're going to do it. 20.5 minus 23.5 and you get 3. Don't write negative 3, that's because of the number that I've taken. 3. 20.5 minus 26. 20.5 minus 26, 5.5. You just subtract this. Now you subtract this. 29.5 minus 20.5. 9.0. I'm doing some mistakes, remember. If I don't add a 0.0, that's a mistake because they've told me that I have to write it till 1 decimal place. 20.5 minus 31.5. 11.0. 30.5 minus 20.5. 10.0. 29.0 minus 20.5. 8.5. 27.5 minus 20.5. 7.0. 26.5 minus 20.5. 6.0. Okay, done. Plot a graph of the temperature change on y-axis against the volume of y on the x-axis. Draw a line of best fit through the points where the temperature change is increasing. Draw a line of best fit through the points where the temperature change is decreasing. So you have to draw 2 lines of best fits. Remember this. Extend both lines so they cross. No worries at all. So we have the volume of y that's given to us, and now we have to write the heading temperature change on the y-axis. Degree Celsius, and then we're going to start. Look at the highest value we have. Highest value is, I guess, 11 we have, and the lowest is 0. So 0 0 1 2 3 4 5 6 7 8 9 10 11 12 and 13. I guess that's fine. 1 2 3 4 5 6 7 8 9 10 11 12 and 13. Okay, in order to make this more precise and to make it more better, I'm gonna suggest you one thing. Do this thing if you want no, don't want to do it, don't do it. Add a 13.0, 12.0, just to make it a little more like better. I guess you should do this because we're measuring all temperatures to 1 decimal place, so I think this is gonna make it look better. That's why I'm doing it. 0.0. Okay, now what you're gonna do, I'm just gonna plot the graph at 0 at 0. So at 0 we have 0, and then at 5 we have 3, at 5 we have 3, then at 10 we have 5.5, at 10 we have 5, and then please don't think that the examiner is not going to know if I mark it here or here or here. No bro, he's going to see this is 5, this is 6, exactly in between is going to lie your 5.5. Don't examiners are very particular about graphs because they know exactly this is the place we're going to try to cheat him. At 15 it's 9. He knows you very well, so don't try to outsmart this smart. At 20 it's 11. 20 it's 11. So you can see from here to here the temperature increased from 0 to 11, but from 11 to 6 it's decreasing. Do you know why it's decreasing? Because over here till 11 degrees the neutralization occurred, but after this the thing that's we are adding from the burette is in excess, and now what's happening is no neutralization is happening at this point. It's just getting more and more dilute. That's why the temperatures begins to decrease. 25 it's 10. 25 it's at 30 it's 8.5. 30 it's 8, and then exactly in between 8.5. At 35 it's 7. 35 it's 7. At 40 it's 6.0. Okay, done. I have to draw two line of best fit. So one is gonna be for my increasing graph, which is gonna be something like this, and then the other is gonna be for my decreasing graph. I feel like that's the perfect line. So yeah, for here, this one I feel like I could make it a little like this. Yeah, perfect. So now this is gonna be the temperature increase. This where the two lines meet is gonna be my temperature increase at my neutralization point. Remember, that's why we always draw this graph. Find the point on the graph where the two lines cross, determine the volume of y at this point. So what I'm gonna do is now I'm gonna show the examiner that I'm a very hardworking person and that I'm gonna figure it out from the graph like this. So the volume of y at which the two lines cross, simply 20 cm3. X is 1.6 mole per dm cube sodium hydroxide. The formula of sodium hydroxide is this. Calculate the number of moles of hydroxide ions in 25 cm3 of X. That's simple. Moles equal to your concentration times your volume. You know concentration is 1.6 times volume is 25. 25 upon 1000 because we take it in dm cube. Now the formula for sodium hydroxide is NaOH. I think they've given this to confuse you, to check if you use the formula mass over MR, but that's not going to be used. So 1.6 into 25 divided by 1000. 1.6 into 25 divided by 1000. 0.04 moles. Okay, 0.0400 moles. Why have I added two zeros? Because 0.04 is still one significant figures. All my values are up to 3 significant figures. So in order to make it till 3 significant figures, I've added 2 more zeros. Because you know that this 0 is not significant, this 0 is not significant, but these 2 zeros are significant. Okay, bhai. The volume of Y in C is the volume needed to completely neutralize 25 cm cube of X. Use your answers to C and D to calculate the concentration of hydrogen ions. So now we know that 0.04 moles of this is going to react with 0.04 moles of this. So now I know that the moles of my H plus ions are 0.04. Now what do I need? I also know the volume of my H plus ions, that is 20 cm cube. So how do I get the concentration? Concentration equals to my moles divided by my volume. I know my moles are 0.04 and my volume is 20 cm cube, but since I need to take it in dm cube, I divided by 1000. 0.02. So that's 0.04 divided by 0.02 that gives me 2 mole per dm cube as my concentration. Got it? Simple. Don't confuse that we have NaOH and now we just have H and OH. It's an ionic equation. So that Na was here, but it was just cut down because it was on both sides. Okay? Suggest why is added using a burette and not a measuring cylinder. They're always going to ask questions like these. So you always have to tell that a burette is more accurate than a measuring cylinder. Suggest why the temperatures are recorded after 30 seconds and not immediately after mixing. You try the reaction to happen, right? You wait for the reaction to stop happening so that maximum temperature is reached. Otherwise, you're not going to measure the maximum temperature. So you allow the time to pass until the temperature becomes like a little constant. So to allow maximum temperature to be recorded, a student does a series of tests using aqueous solution Q and aqueous solution R. Solution Q is acidic. Solution Q contains one cation, one anion. The test the student does on Q are shown in table 3.1. Some of the observations of the test are shown. You add universal indicator, the color changes. They've told you already that the Q is acidic and it contains one cation, one anion. Add a piece of magnesium ribbon disappears. Obviously, it's acidic. So if you're going to add magnesium, that's a metal, into acid, you're going to form hydrogen gas. Add dilute nitric acid followed by aqueous silver nitrate, white precipitate form. This shows that we have a chloride ion present. Go to the table at the last and see we have an H plus ion present over here. That's the cation, that's the anion. Describe the expected color change in 1. When you add universal indicator to an acid, you get red color. A gas is produced in test 2. Yeah, that's hydrogen gas, because in an acid you have added magnesium metal. Predict one other observation made by the student in test 2. Magnesium ribbon disappears, and since you're producing a gas, so you're going to observe effervescence. Predict the identity of the gas produced in test 2. That's going to be hydrogen gas. Describe a test to confirm the identity of the gas. Include the test a positive result. You know what's the test for hydrogen gas? It's written at the end. You use a lighted splint, and the observation is it extinguishes with a pop sound. This pop word is important. Identify the cation and anion. Cation is H plus ion and anion is Cl negative. So that is hydrochloric acid that we're dealing with. Done? The student does a series of tests on R. Some of the observations are shown. 4, we do a flame test. We get a blue-green flame. That means we have copper present in it. Because go to the table and look at the flame test. If you have blue-green, then you have copper 2 plus ions present. Add aqueous ammonia dropwise until change is seen. Light blue precipitates. Now, since we have copper, you add an excess. You have a blue precipitate. Describe how the student does a flame test. Flame test is very easy. What you do is that you dip a wire in the solution. So this is your solution that contains copper 2 plus ions. You dip a wire in it, and then what you do? You take a flame, the blue roaring Bunsen burner flame, and you put your wire that you've dipped into the solution on the flame, and then you get the test. So it's simple. Dip a wire into the solution, then put the wire on a blue roaring Bunsen burner flame. That's all. Describe one additional observation expected in test 5 based on the observations in 4 and 5. Okay, so we have to write one observation. Okay. Blue precipitate dissolves to form a darker blue solution, because we know that when copper precipitates dissolve in ammonia, they form a very dark solution. If you do not know this, learn it from the table, and moreover, you given table at the end, you can see the table as well. Dark blue solution forms. That's a very important test. Okay, describe one additional test to confirm the identity of the cation in R. Include. Okay, so basically over here, the cation that we're dealing with in R, we're gonna add sodium hydroxide. How do you do this? You know that for cation test, we add one reagent is ammonia and the other reagent is NaOH. So we add NaOH in first dropwise and then in excess. So NaOH aqueous we add, and then the results are going to be light blue precipitates insoluble in excess. Don't forget this. Insoluble light blue precipitates insoluble in excess. Identify the cation in or. No worries. Copper 2+. Done. Okay. Now we have the 6 marks question, which says alcohols are used as fuels to heat water. Plan an experiment to determine which alcohol, methanol or ethanol, releases more thermal energy per gram of the alcohol burned. Okay, so that's the alcohol, that's the burner. We have to plan the amount of energy. So we're going to heat water, and then we're going to see how much temperature of the water increased. First, we're going to take equal amount of ethanol, then we're going to take equal amount of methanol, then we're going to heat water with it, and the water in which there's a greater temperature increase, definitely that's going to release more thermal energy. Okay, your plan should include the use of alcohol burner as shown to heat water. You should use water, ethanol, common laboratory apparatus. No, the chemical should be used. Easy. Your plan should include the additional apparatus needed, the method used, and how the measurements are used to determine alcohol releases more energy. Okay, over here I'm going to tell you something important. Basically, your mark schemes are based on these 3 points. If you address the 3 points, the apparatus, the method, and the way you're going to determine, you're going to get your marks. You may draw a diagram to help answer your question. I am definitely going to draw a diagram, because if I don't draw a diagram for the experiments, I don't get what's happening. So I'm going to draw a diagram, then show you how I've planned it. Realized a very important word over here that we need to realize: the temperature changed per gram. That's why the method that I've designed, and it's a little interesting, you got to do is, first you got to measure. I'm going to tell you the method and you just write it in your own words and then see the apparatus. First, you're going to measure the mass of your ethanol or methanol or whatever you are taking. First step is going to be this: you measure the mass. The second step is going to be you take water and you take a fixed volume. So use a measuring cylinder and transfer it into a beaker. Third step is going to be you measure the initial temperature of the water using a thermometer. Okay? You measure the temperature of the water using a thermometer, because there are 2 things you need to figure it out. I tell you there are 2 things. The first thing is you need the change in temperature, and you need to divide the change in temperature by the mass of alcohol. Why do you need it? Because you need how much degrees Celsius changes per gram of the alcohol. How much degrees Celsius of water is going to be raised by 1 gram of alcohol. So you measure how much of your alcohol is used and how much change of temperature it can cause. That's the thing over here. So first you measure the initial mass of your alcohol, then you take the water, measure the initial temperature, and after heating it, you measure the final temperature of water. And then you subtract the 2 temperatures and get the change in temperature. And then you measure the final mass of the methanol or ethanol that's left, and then you subtract the mass of the ethanol and get the change in the mass of alcohol that you use. So that's what you're going to do. Initial mass of alcohol minus final mass of alcohol in the denominator. Initial temperature minus final temperature in the numerator. Change in temperature upon the mass of alcohol that's used is going to give you the change in temperature per gram. And then the more the change in temperature per gram, the more energy your alcohol is releasing. So how are you going to put it in words? For the apparatus, you're going to write a mass balance, whatever you call it, a measuring cylinder, a thermometer, and a beaker. So apparatus done. The method you're going to tell them is that what do, you measure the initial mass, then you transfer a fixed volume of water, you measure the initial temperature, you heat the water, you measure the final temperature, you measure the final mass of the alcohol. And how do you determine it? The third step is gonna be that you use the formula, you subtract the initial temperature and the final temperature to get the change in temperature, and then you subtract the initial mass of the alcohol and the final mass of the alcohol to get the mass of alcohol that's used in burning, and then you divide the two, and then you get how much energy is released per gram. And the greater the temperature change per gram, the more thermal energy is released. That's all.